Today I intend only to cover this last problem in your notes here, and maybe you've been tracking along with me on B courses. And so in all likelihood, we'll have an abbreviated lecture today. So the last example problem I want to talk about in the context of small elastic and plastic deformations is a problem of crack tip plasticity. This was an example worked out decades ago by people named Holt and McClintock. McClintock was a well-known professor at MIT in mechanical engineering. And if you study, for example, fracture mechanics in elasticity, you are familiar with the notion that the stress is predicted to become unbounded as you approach a crack tip. And that's an artifact of a couple of idealizations. First being the idealization that a crack is mathematically sharp, so that the radius of curvature at the crack tip is infinite, number one. And secondly, an artifact of the use of linear elasticity to make the prediction. Why linear elasticity? Simply because it's tractable. And it's has a very well documented empirical basis. And so what people do in fracture mechanics is they push linear elasticity beyond its intended limits and simply live with the contradictory conclusion that the stress and the strain become unbounded at a crack tip. And of course, that's unsatisfactory. Plasticity has the effect of restoring some logic and sanity to the whole discussion, in that the prediction of infinite stress at a crack tip is, of course, modified by the presence of plasticity. What you have instead, as you can imagine, is yielding of the material in a ductile material like a metal, yielding at the as you approach the tip of the crack. So I'd like to discuss that phenomenon as we have both elasticity and plasticity operating. I'd like to discuss it in the context of anti-plane shear, which we've briefly studied before. Why? Because it's a mathematically relatively simple setting in which to illustrate the phenomenon that we're trying to highlight here. So let's do a quick review of our earlier work on anti-plane shear, where we were talking about perfect plasticity with no elastic strain. We had the solution of this form, that the deviatoric stress tensor looked like this: a tau hat vector, tensor product k plus k tensor product tau hat. K, of course, is the unit vector pointing out of the screen. And the flow rule told us then that this lambda tau hat, this vector, you can think of this is a vector consisting of T, say 3,1 and T 3,2, the transverse shear stresses. Lambda, the scalar field that has to be non-negative in an actual solution, times tau hat is a half the gradient of the velocity. Previously, I referred to the velocity as W, but today I want to use W as for displacement, so W dot will be the velocity. Tau hat, we deduced before, is K, the yield stress and shear, times the unit vector, which in equilibrium with no transverse pressure gradient in the z direction satisfies div t equals 0. So it's a unit vector field which is divergence free. And earlier we found a solution that, say, t is directed along the azimuthal direction, E phi, that has 0 divergence. And under those assumptions, the pressure was entirely 0, and therefore the stress was entirely deviatoric. So continuing with that recap of the discussion we had previously, we found that this equation implied that theta, which is the angle between t and E1, that theta field is constant on the so-called beta lines, which are defined as the trajectories that satisfy this equation. And so those beta lines are straight. And they make an angle of theta minus pi over 2 with the x-axis. The alpha lines were the t lines. They make an angle of theta. And the beta lines are their orthogonal trajectories. Okay, so if you remember our earlier example of a stress-free, retraction-free circular hole surrounded by yielded material, the alpha lines were purely azimuthal and the beta lines were radial. So they're straight lines, but of course they're not parallel because the rays through the origin, while straight, are certainly not parallel. Okay. So again here, in our earlier discussion, T was azimuthal as it turned out in that solution. We'll restore that solution here and see if we can use it again. And the S trajectories, the orthogonal trajectories, that was minus ER, right? And this phi here was theta minus pi over 2, that the angle made by the beta lines with the horizontal. So all of this was for the case of rigid, perfectly plastic material. But there's nothing in this that disallows possibility of an elastic and a plastic deformation. We just have constructed an equilibrium field, stress field. Let's see if we can construct an elastic and plastic strain field that are consistent with this equilibrium stress field. So again, previously we'd made no restriction to small deformations either, but in this case we will, and invoke this approximate decomposition of the strain, the symmetric part of the spatial displacement gradient, into elastic and plastic parts, epsilon sub e, epsilon sub p. Epsilon sub e satisfies the usual strain-stress relation, and the dot of epsilon sub p is given by the flow rule. Okay. And naturally we'll assume a displacement field of anti-plane form, some scalar field W, a function of in-plane coordinates x and y, along k. That's consistent with our discussion, our assumption that the velocity field is also, W dot along k, obviously. Let's here suppress the time dependence for now. The spatial displacement gradient then is just k tensor product gradient W, where that gradient is two-dimensional. The strain is the symmetric part of that, that's here. So just as we decomposed the deviatoric stress before in this form as some two-dimensional vector tensor product k and the transpose plus the transpose of that, we can do the same for the strain field under this assumption of anti-plane displacement. The strain field can be decomposed as k tensor product epsilon hat plus epsilon hat tensor product k, where epsilon hat is a vector, which is just half the gradient of the anti-plane displacement. Okay, let's see if we can use the tau that we had previously. Insert that in the elastic strain stress relation. That tau is purely deviatoric, so the strain stress relation will pick up only the deviatoric part of tau. Okay, which involves just the shear modulus. And because tau has that decomposition similar to this in terms of tau hat, tensor product k, and so on, the elastic strain will have a similar decomposition, where this epsilon hat now is a vector, which is 1 over 2 mu times the stress vector tau hat. So anything with a hat on it is a vector, whereas tau and epsilon without the hats are tensors. Also, because of the structure of tau hat, the same kind of decomposition, the flow rule tells you that the plastic strain rate has the same kind of decomposition, where in terms of a vector epsilon hat p, whose dot is lambda tau hat. Let's proceed as we did in earlier examples, and suppose that tau hat is fixed independent of time, right? And fixed at what, you might ask? Well, fixed at this value. Tau hat is the stress K, yield stress and shear, times T, where T satisfies this divergence condition. And again, we had an example before in which that T was purely azimuthal. Okay, so let's suppose tau hat remains fixed. Then we can integrate the flow rule in time with tau hat fixed. We just get some scalar in front whose time derivative is this lambda, right? Then we can reconstruct the total strain field, elastic part plus the plastic part. The only thing interesting about that is it's some scalar coefficient, I'll call it psi, times tau hat. And therefore, since epsilon hat, the strain vector, is 1/2 of gradient W is twice that scalar times tau hat. Tau hat is KT. So we deduce, as we did in the rigid plastic case, that W has no directional derivative along the trajectory orthogonal to T, namely the S trajectory, which means that it's a constant on the so-called beta lines, right, with unit tangent S. Okay, so let's re-examine our earlier explicit solution in which T was purely azimuthal. We had plus or minus here. Let's look at the plus solution. T is E phi, a function only of phi in a polar coordinate system. So here's polar coordinates. Remember, the beta lines were straight. We can take radius as the parameter, the coordinate along the beta lines if we want. The alpha line, the alpha trajectories with unit tangent T were concentric circles. We can take the coordinate alpha, we can identify it with phi, right? So we can identify the beta alpha coordinate system as just the polar coordinate system in this case. Okay, so S is aligned with ER, so then this condition says that ER dot gradient W is 0, which means W has no R derivative, and therefore the gradient of it in a polar coordinate system just picks up the phi derivative, and that's an ordinary derivative because of this condition. Okay, so we have some information about the gradient of W, and hence we know something about, well, since this epsilon hat is 1/2 the gradient of W, we have some information about it. For example, epsilon hat, which is just 1/2 of this gradient W, if you look on a beta line where phi is constant, everything with phi constant along a beta line, if you just look along a beta line, this varies inversely with radius, right? So the strain is monotonically decreasing in magnitude along a beta line. So the farther out you go along a beta line, the less the strain becomes. Remember that the stress, tau, is also constant on a beta line, right? Because tau hat, the stress vector, is K, a number, times this T. On a beta line, phi is constant, so the stress vector is constant on a beta line also. Therefore, from the elastic strain-stress relation, the elastic strain vector is also constant along, also constant along a beta line. But the total strain is monotonically changing along a beta line. So the plastic strain vector, which is simply the difference between the total strain vector and the elastic part, that has to be varying monotonically on a beta line. Okay, it's monotonically decreasing. So we can imagine there's going to be a boundary between the elastic and plastic solutions that looks like this. The plastic strain, say take array, a beta line, the plastic strain varies monotonically, decreases monotonically until it's 0, let's say, and at that point you're on the boundary between the elastic and plastic regions, right? In the elastic region, there's no plastic strain at all. In the plastic region, of course, there is one, but it varies monotonically and decreases. So there'll be some, on a given beta line, there'll be a certain radius at which the plastic strain vector diminishes to 0. And a beta line corresponds to a fixed value of phi, the azimuthal polar coordinate, right? Let's say here, let's take this ray here, this beta line. So there'll be some radius, call it r at that phi, corresponding to that beta, corresponding to this particular beta line, at which the plastic strain is 0. And as phi changes, you're on different beta lines. The radius at which the plastic strain becomes 0 can then vary with phi. So you have a plastic zone that, at least qualitatively, looks like this. Right? If we look at, here's our crack here, and we're looking at the application of our previous solution, purely azimuthal t trajectories, that is, the alpha trajectories are concentric circles, and seeing if that can furnish us with a solution. Well, so the logic then has led us to this conclusion that there should be some boundary. We don't know its shape yet, which looks something like this. We have no idea about its precise shape. But the boundary between, that separates the elastic zone, say exterior to this region, and the plastic zone in the interior here. So think that this is symmetric about this axis, let's say, right? X-axis. That boundary should somehow, is parameterized by giving radius as a function of phi. So it gives you a curve depending on the parameter phi. Okay. Now this theta, if you take theta and subtract pi over 2, that puts you on a beta line, where the angle with the horizontal here is phi. So that tells us theta, which is part of the stress state, right? That's the orientation of the t trajectory. That tells us theta, it's in terms of the coordinate phi. And because theta is constant on a beta line, of course phi is also constant, we've been through that already. While r is constant, then on the orthogonal trajectories, the alpha lines correspond to curves where r equals constant, and those are concentric circles, sketched here. And then just to recap, r of phi is the radius of the elastic plastic boundary at the angle, azimuthal angle phi. So our job is to find, we've constructed already a solution in the plastic zone as far as the stress state is concerned. To find the deformation, let's see, we have to do a little more work to find the actual deformation. So let's see how that works. Okay. Okay, so here we are. Here's our gradient of W. W is independent of radius in the plastic zone. So the gradient looks like this. We've deduced previously that that's some scalar times t. So comparing, since t is E phi, comparing these equations gives us this. And the total strain vector looks then like this. We don't know anything about the coefficient psi at this stage. So here again is the geometry we're looking at, and we're trying to find this radius that divides the plastic. By plastic, I mean a region in which you can have both elastic and plastic strains coexisting, whereas the elastic region, there's no plastic strain. Okay, well, as R tends to capital R of phi from within the interior of the plastic region, we know that the strain will tend to the elastic strain because the plastic strain is diminishing to 0 at this limit. The elastic strain, however, is 1 over 2 mu times the stress vector tau hat, which we know is KT. So let's see, we know the strain. It is, let me back up here. The strain vector is 1/2 gradient W. As R approaches R, capital R of phi, with the 1/2 incorporated, we have this from the total strain. And that has to equal this, which is K over 2 mu times E phi, right? There's an E phi here. So we just get this equation. This tells us, if only we knew this radius R of phi, we would be able to integrate this equation to get the displacement field in the plastic zone. So everything hinges on R of phi. Once we get that, we simply perform an integration and we get the displacement. How do we get R of phi? Well, R of phi is the limit, is the boundary of the region in which norm tau hat is equal to K, right? We have a perfectly plastic material, so norm tau hat is equal to K everywhere in this interior. That's the solution we've constructed so far. And that, by traction continuity, then, should tell us that that's going to match the elastic solution, the tau hat from the elastic solution at this boundary. Okay, so let's see how can we do that. So let's take the step back for a moment. What we're doing is we're imposing a matching condition in stress space. We're going to match the plastic solution, where norm tau hat is equal to K, to the elastic solution by imposing this condition on the elastic solution. And we do that for the purpose of locating a boundary, a position vector in the xy plane. Okay. So we're finding position in terms of stress, in effect. And that suggests that we might as well work in stress space to begin with. That is to say, we might as well try to find a formulation in which we can, instead of solving for stress in terms of position, let's solve for position in terms of stress. That brings to mind something we did before called the Hodograph Transformation, in which we interchange the roles of the dependent and independent variables. So instead of regarding x and y, or x1 and x2 as the independent variables, we'll work with the formulation in which, say, the components tau hat 1 and tau hat 2 in a orthonormal basis, we'll take those to be the independent variables and see what we can do. So here's one equation that we have to work with. The equilibrium condition has to apply everywhere. And the 1 and 2 refer to Cartesian components. If we want to interchange the roles of the dependent and independent variables, let's use the chain rule to write the differentials of the tau hat components in terms of the differentials of the coordinates, the x1 and x2, just the chain rule as usual. Let's call that matrix T. And likewise, we can write the differentials of the coordinates in terms of the differentials of the stress components, again by the chain rule. Call this matrix R, and then this has to be the inverse of this T, right? So we see that the divergence of tau hat, which has to be 0, that's the sum of the diagonals here. That's the trace of this T vector, this T matrix, I should say. Let's have a look at the divergence of position X in tau space. That is, I'll call that, I'll write a capital D divergence so you don't confuse it with this kind of divergence in X1, X2 space. The divergence of position referred to stress space, that's just the sum of the diagonals of R, it's the trace of R. So having a differential equation I know is satisfied in X1, X2 space, namely div tau hat equals 0, I'm trying to look for a differential equation for X that's satisfied in tau hat 1, tau hat 2 space. Okay, so the column vector dx, which consists of dx1 and dx2, is the inverse matrix then of T times the column vector d tau hat, consisting of d tau hat 1, d tau hat 2, and that's the same as r d tau hat, right, the column. So let's look at, let's compute R by inverting T. That's easy, it's a 2 by 2 matrix, easy to invert. Div X in stress space then, that was the trace of R if you recall, right here. It's going to be 1 over, so the trace of R is 1 over the determinant here times the sum of the diagonals, which is the divergence in X1, X2 space. That is already 0 from equilibrium, so indeed, position X has 0 divergence in stress space. We can write the total strain vector in terms of Cartesian components. They'll be given this way, because epsilon hat is the gradient of W, so the Cartesian representation is this in X space. Because epsilon hat is itself a gradient, of course it has 0 curl. In other words, this equation is satisfied. The two-dimensional curl is 0. D epsilon 2 hat dx1 minus d epsilon 1 hat dx2 is identically 0. That's just from the equality of the cross partial derivative, the second derivatives of W. So we know that the curl of the strain is 0 in X space, where the curl is taken with respect to position, X1 and X2. In the elastic region, so we have the solution in the plastic region, most of it anyway. In the elastic region, the stress vector is twice the shear modulus times the strain vector. So if just multiply this equation, curl epsilon hat equals 0, multiply through it by 2 mu, and you have that the curl of tau hat is also 0 in X space. In other words, this is true. We can relate that to the curl of position in stress space. Let's look at dx2 d tau 1 minus dx1 d tau 2. That's the curl of position vector X in stress space. Let's see. Let's go back here. That's this. It's this minus this. The difference of the off-diagonal components. But according to this inverse, we can relate that to the difference of these off-diagonal components with a 1 over det p in front. So we get this expression. We've just gotten through showing that this parenthesis is 0. So indeed, the curl of position in stress space is also 0. Okay, that's enough to assert that there's a function, scalar function, of position in stress space, which is we'll take tau hat vector to be the position vector in stress space. Okay, there's a scalar, there has to be a scalar value function of tau hat such that x is its gradient in tau hat space, the gradient with respect to the stress components. Okay, that comes from this. We have the other condition that x also has 0 divergence in stress space. So we have div of gradient f equals 0. In other words, the Laplacian of f, this function f, whatever it is 0 in stress space. Okay, so let's have a look at the geometry in stress space. So tau 1 and tau 2 are the coordinates, if you like, in stress space, replacing x1 and x2. You can use the same Cartesian orthonormal basis. Excuse me. And it's natural then to take the norm of tau hat to be the radius in stress space. Remember, tau hat was aligned with the unit vector t, which in turn was oriented by this angle theta. So naturally, we should take theta as the polar angle in stress space, not phi. That's different. That differs from theta by pi over 2, if you remember. But we could write tau, position in stress space, as its norm, the radius tau, aligned with the unit vector t of theta. Okay, so we're effectively using polar coordinates in stress space. Okay. Then the Laplacian in stress space is just the usual polar coordinate formula for the Laplacian, which you can quickly derive if you don't remember it. Two derivatives with respect to radius, 1 over radius, the f d radius, 1 over radius squared, d squared f d theta squared. Okay, so what conditions do we want? We want, so we're in the elastic region. We're trying to find a solution in the elastic region here, right? So you recall, because we use this elastic constitutive relation. In the elastic region, we can do this because there's no plastic strain. Right? At the elastic plastic boundary, we want to match our stress with the stress that we know comes from the plastic solution. Yield stress and shear times the same T. And the elastic plastic boundary is defined in X space in terms of its radius, which will be r of phi at the boundary, times ER of phi, where phi is the azimuthal angle in X space. ER was minus S, if you remember. Right? So let's see. If you take a dot product of this X with T, which is orthogonal to S and hence orthogonal to ER, you should get 0. And the norm, tau, the radius in tau space should be K, right, at the elastic plastic boundary. Okay, if you've done any linear elasticity at all, if you've taken a course in fracture mechanics, I'm asking you to take this on faith if you haven't seen any linear fracture mechanics. In linear elasticity, the stress asymptotically behaves like 1 over the square root of radius as radius tends to 0 as you approach the crack tip. So that's, I think most of you have heard about that kind of thing. And this is where elasticity, of course, gets in trouble, because with the stress blowing up like 1 over the square root of radius as r tends to 0, the strains will as well in linear elasticity, and then you're outside the range of the application of the theory that you use to make the prediction. So you have a logical inconsistency. Nevertheless, outside the plastic region, the plastic region is effectively intervening between radius going to 0 and the elastic solution, right? So the elastic solution cannot get all the way down to r equals 0 because of the intervening plastic zone. Nevertheless, we would expect, for a small plastic zone, the elastic solution is perfectly meaningful in the remainder of the material. So from linear elasticity, we would expect the stress to scale like 1 over square root of radius with some constant, with some angular dependence in front, trigonometric dependence on phi, and some constants also, right? But the radial dependence goes like 1 over square root of radius. So as r tends to 0, tau blows up, or you could think as this is saying, as tau gets small, radius blows up. So the inverse of this is that r scales like 1 over tau squared, right? As tau gets small. So you would expect then the norm of position, which is radius, to scale like 1 over tau squared near the origin in tau space, in stress space. So here I'll simply write down the Halton-McClintock solution position in terms of radius tau and angle theta in stress space. And then we'll simply confirm that it is in fact the solution that satisfies all the conditions of our problem. So here R naught is just a constant that we'll have to determine. K is the yield stress and shear, tau is radius and is the norm of tau hat, that's the radius in stress space, theta is the azimuthal angle in stress space, and T and S are the same vectors we had before. T of theta, S of theta. Let's check to make sure that our conditions are satisfied. So for example, at the elastic plastic boundary, we want tau, the radius in stress space, to be equal to the yield stress and shear, right? So let's put tau equals K, then this parenthesis disappears. This becomes a 2. We have a minus 2r naught sine theta along S. Minus S was ER phi, if you recall. And we get 2r naught sine theta. Remember that theta and phi are related by this. Theta is phi plus pi over 2. So we can replace theta by phi plus pi over 2. That gives us x is some function of phi times ER phi, which, and that function will then has to be our capital R of phi, which is the radius of the elastic plastic boundary at azimuth phi that we've been looking for. You see quickly then that R of phi has to be 2r naught cosine phi with this. Okay. So now we know R of phi, but we still don't know R naught. Okay. With R of phi known, apart from the constant R naught, we can go back a couple of pages and integrate this equation now to get the displacement field in the plastic region. So you can see this fairly intricate solution, even though the problem looks simple. Okay, we also now know that, interestingly enough, the shape of the elastic plastic boundary, because R of phi, given by this, that tells you that the elastic plastic boundary is in fact a circle. A circle centered at x and y equals r naught and 0. This is the equation of a circle, although we're measuring radius from here. it's a circle centered at R0, okay? So when phi is pi over 2, for example, the radius is down here at 0. When phi is 0, the radius is twice R0. You can verify that everywhere, for other values of phi, you get this circle. Okay. So here's the T and S, as we indicated. R of phi now is known. So that's interesting. Okay, we're not done with this solution. We have to check that, in fact, there is a scalar field F whose gradient is this position x that we've just written down in stress space. In stress space, we're using radius, tau, and angle theta as the polar coordinates. So we need to verify that there's a function f of tau and theta whose gradient is this x we've just written down, which moreover has to have 0 Laplacian. So let's verify that. Well, if this were true, then it would be true that the differential of f would be grad f dot d tau, right? Grad f of tau dot d tau. That's just the definition of gradient. And grad f, we're saying that we're checking the assumption that grad f is x, so that would be x dot d tau. Tau is the position vector in stress space, which is the radius scalar tau times the unit radial vector, which is t of theta. D tau then is, d tau vector is d tau radius times t plus s dt, which remember is, tau dt. dt was s d theta, if you recall. So take the x that we have above, which is written in the TS basis, and dot it with this expression for d tau, and you'll get this expression for df. Okay? In terms of d tau and d theta. So if there is such an f, it must be the case that this coefficient with the cosine must be df d tau. And this coefficient with the minus r naught in front times tau it looks like I'm missing the tau in this. That must be, yeah, so insert a tau here somewhere. R naught, yeah. There should be a tau. That's a typo here or a misprint. There's a tau sine theta sitting right here. And that must be df d theta. Okay? And even though I've made a transcription error here, you can still verify that the equality of cross partials is verified. In other words, if you take a theta derivative of this and take a tau derivative of this, you'll get this equality. So that confirms that there does exist an f whose gradient is this x. What remains to confirm is that the Laplacian of that f is 0. With these expressions for df d tau and df d theta, you can verify these statements here. D tau of tau df d tau is this. That's also minus 1 over tau d squared f d theta squared. So I'm reinstating the tau that I mistakenly omitted here. Okay. So that if you add these together, and notice that the result is just tau times the Laplacian, you'll get 0 at all values of tau. Therefore, the Laplacian of f is 0 as required. So we do have a solution. Okay. To interpret it, let's post-process this solution a little bit. Let's introduce polar coordinates centered at this point R0, which is the center of the circular disk that describes the plastic zone, right? So let's put instead of using polar coordinates centered at the crack tip, let's use polar coordinates centered at this point, right, R0. So we'll use a different radius and a different azimuth. I'll call the radius, instead of calling it r as we did before, I'll call it r1. Instead of phi, I'll call it phi1. So these are coordinates. And t, remember, was perpendicular to r, the radial vector from the crack tip, located at angle theta. And that had this representation, S had that representation. And let's look at the position of a point relative to the center of this disk. That disk is located, in terms of our original basis, it's located at r0 times e1. And x1, which would be this vector, is that vector minus this vector, right? Because this vector is the sum of these two. And we have x then minus r0. I can decompose e1 into the ts basis, and you can confirm for yourselves that when you do that, you get e1 is cos theta t minus sine theta s, with the r0 in front. If you look at the result for x that we wrote down, this Halton-McClintock solution for x, and form this combination, you'll get this. Tau, again, is radius in stress space. You could reinterpret this in E1, E2 basis by writing T and S in this way, and you'll get this. And so that suggests that we, if we now introduce polar coordinates for this vector x1, running from r0 to a generic point here, the radius would be r1, the azimuth would be phi1. So as usual, the E1 component of x1 would be r1 cos phi1, the E2 component would be r1 sine phi1. Okay. So by putting this on the left and equating two sides, and you have a trig identity, a couple of trig identities, you get r1 cos phi1 and r1 psi phi1 in terms of tau and theta. And of course, you square these and add to get rid of the phi1 terms to get this. And then take the ratio to get the tangent, and you'll get this. So phi1 is just twice phi, as you expect, just from the diagram. Okay. So this makes things a little easier to use this new polar coordinate system, because it gives the radius easily in the new system in terms of the stress intensity, right? And the phi1 is 2 phi, okay? So here before we had ER at phi, E theta, E phi at phi. We can look at ER at phi1 now, that's this vector, and E phi at phi1. In between them will be an angle gamma, which is the difference between phi1 and phi, which is just phi itself, which is phi1 over 2, okay? Having that, we can write our stress vector in terms of components in the new basis, ER at phi1 and E phi at phi1. And that stress vector has components, say, TZR and TZ phi, except we're in the R1 and phi1 coordinate system. Right, we just have these anti-plane shear stresses components. And the z-axis is just coming out of the screen. We know that that's equal to tau times t, where t itself is E phi at phi, not phi1. So we should then decompose E phi at phi in terms of the phi1 basis, ER at phi1, E phi at phi1. From the diagram we just had, you can see that will involve the angle gamma, which is phi1 over 2. So we can conclude then from this that TZR1 is tau sine phi1 over 2. PZ phi1 is tau cosine phi1 over 2. Where tau we can solve this for tau in terms of R1 easily. Tau is K root R naught over R1. So TZ R1 is this. Here you have a 1 over square root of R singularity, but the radius is R1, and we have this angular variation, TZ phi 1 is this. Well, if you took a course in linear elasticity, one of the simpler problems you would solve is the antiplane elastic field near a crack tip, the asymptotic structure of the antiplane stress field as you approach a crack tip. That asymptotic meaning the dominant terms that emerge as the radius tends to 0. Okay, and those have exactly the same structure, the same angular variation, psi phi 1 over 2, cos phi 1 over 2. For example, in ME 225, we discuss solutions like this, fracture mechanics, or in 282. So my apologies if you haven't seen this before, but this is a well-established result. You can easily look up on your own. And this brings in the famous notion of so-called stress intensity factor. So the asymptotic structure of the elastic solution is, I call it K, a constant called the stress intensity factor, over root 2 pi R1, has the same R1 variation and phi 1 variation. K is called the mode 3 stress intensity factor. Mode 3 means antiplane shear. Mode 1 means an in-plane opening of the crack. And mode 2 means an in-plane shearing of the crack. Okay, in-plane shearing. And people who work in fracture mechanics are experts at figuring out what this constant K is in terms of other conditions that have to be given in the problem. For example, the problem as we set it up so far is just a semi-infinite crack and no other conditions being assigned. Those conditions that we've left undiscussed so far can be used to determine the value of the so-called stress intensity factor. So the stress intensity factor can be computed, if you're a clever elastician, from the conditions that pertain remote from the crack. For example, you're loading a block of material away from the crack in the far field, away from the crack, and other geometric data pertaining to the body. So a linear elastician or a fracture mechanician would tell you, for a given problem, would compute K3 for you, or K as we're calling it. So you could regard K as known. And then by comparing this solution with the structure of the solution we've just found, which involves the size of the elastic plastic zone, the radius of that circle, you could deduce that that radius is here, given this way, in terms of the stress intensity factor, capital K, squared over 2 pi shear, yield stress and shear squared. And of course, this is a positive number, as it had better be, because R naught had better be positive. Okay, a simple example that comes to mind where the stress intensity factor is easy to compute is, say, a small crack in a large block of material. By large, I mean, let's suppose that the external boundaries of the material are so far away from the crack itself that you can regard the external boundaries as being off at infinity. Position goes to infinity and radius goes to infinity. And suppose that remote from the crack, so there's a boundary here on top far away, and we're loading it, we're prescribing an anti-plane shear traction coming out of the screen at you. So that's the tip of an arrow here coming out of the page. And we'll say that that prescribed value is tau infinity, meaning this is a constant corresponding to the traction in the far field that you're prescribing, far away from the crack. Whereas T31, which would be the anti-plane stress on a boundary, the vertical boundary, let's say is 0 far away from the crack. For equilibrium then, you have to have an anti-plane shear traction pointing into the page here below the crack in the far field, right? So you maintain equilibrium. So that's the tail of an arrow here, the same time infinity. For this case, the stress intensity factor is relatively easy to get and is well known. Say A is the half crack length, so 2A is the length of the crack. We'll center it here, put its center right at the origin of coordinates. K is this prescribed far field stress times root pi A, where A is the half crack length. Then that tells you the size of the plastic zone in terms of the assigned far field stress. Okay, so for example, if you increase, as you would expect then, if you increase the value of the far field traction, the intensity of it, you're going to increase the size of the plastic zone. If you decrease it, you'll decrease that size. Okay, so that summarizes the Hult-McClintock solution, which you won't find in textbooks, and is perhaps more interesting than the examples that we discussed last time, which are for the simple reason that those are very extensively discussed in all the standard texts on plasticity. This one, however, is harder to find. Okay, so there's a paper by Hult and McClintock that goes back decades, I think in the 1950s actually, where they discuss this solution in detail. And that's essentially just about the only explicit solution that's known for elastic plastic fracture. There's some results in plane strain, but as we've seen before, but they pertain to the rigid, perfectly plastic case, whereas here we're including the effects of elasticity. Okay. All right, and so in homework, I'm going to ask you to verify that the solution we construct is admissible from the standpoint of dissipation. In other words, that scalar field lambda that appears in the flow rule is in fact non-negative in the plastic zone. By plastic zone, I mean a zone in which you can have both elastic and plastic strains existing. So in your upcoming, the next homework will be the last homework, and I'll ask you to verify that. Okay, let's stop here today. As promised, this is an abbreviated lecture today, unless there are some examples, or rather some questions, I should say. Okay.
Professor, can I ask you a question?
Yeah.
And what about mode 1 or mode 2? Because as I remember from mechanical behavior of materials, we have the same plastic zones for all of the modes. I do not know, is this an assumption? Is this some mathematical finding?
No. Here, this plastic zone, the circular plastic zone, is peculiar to anti-plane shear.
Okay.
Yeah, in mode 1, for example, you'll have something similar to what we had before. In the rigid perfectly plastic case, we called it the Prandtl solution, where we had centered fan and so on, but it's modified by the presence of elasticity.
Yeah.
And it's a much more challenging problem.
Yeah.
So this shape of the elastic plastic boundary is part of the problem.
Yeah.
To be solved, right? So the circular shape is specific to anti-plane shear. And in fact, if you have hardening of the material, here we had elasticity with a definite modulus and then perfect plasticity. If there's hardening after yield, then it turns out that's a substantially more difficult problem, even in the anti-plane case. You'll still have a circular boundary between the elastic and plastic regions, but the plastic zone will engulf the crack tip. The crack tip won't be on the boundary. It'll be interior to the elastic plastic region. Yeah. That's a substantially more difficult problem, and you can find some research papers on that. Yeah. So we made no assumption concerning the shape of the boundary between the elastic and plastic zones. We derived it. Okay. Okay, if there are no more questions, then I'll see you all on the other side of the weekend.